Okay, so this is going to be interesting because I actually don't have any slides, but I'll explain in just a minute. Some of you may be familiar with, hold on, let me get this started with this site. It's a little difficult to do this while holding a microphone, but we'll see. Okay, so I don't know if anybody's really familiar with the site, but I've written 2 books on Modelica. The second one is freely available on the web. You can find it over here, but that's not the topic for this talk. The topic for this talk is this thing over here, which is this Modelica playground. So there's a URL there that you can go to. If you're watching this remotely, maybe hold off on using the site while I'm doing this, just so that it doesn't slow anything I'm doing down. So that's just a polite request there. So this isn't very interesting. It's just a blank page. I'll come to that in a minute. But the point is, you can, yeah, we'll talk about what this does in a second. So I'm going to actually show you some content, and how that's done, I will explain in just a moment. But just bear with me while I copy a few things. Again, for the moment, I encourage you, do not do this at home. So just a second. What I'm going to do is jump into my presentation directly from this site. Okay, so now we're looking at the presentation I'm going to give. So the first thing I'm going to start off with is I call this Modelica playground. I'm not sure everyone's totally familiar with this concept of a playground, so I'm going to just talk about that a little bit. There are a lot of languages out there that have such playgrounds. They're just areas where you can go and write code in that language without having to, install any tools or compilers or anything like that. Presentation cannot be seen. That is true. It cannot be seen because I haven't shared it. So just 1 minute. Thank you for that. Let's see. Share. Just a sec. Sure. The whole thing. Okay. Hopefully that rectifies that problem. Again, thanks for pointing that out. Okay. So just the first slide again. So playground. So the thing was, I program in a lot of languages, and it's really cool to play around with them in these playgrounds. A lot of times I just quickly go somewhere and try something out. That it's very convenient. And we didn't really have one for Modelica, so I thought, okay, I should build one. The main reason, it's a funny little backstory, the main reason I built it actually was because my daughter is an engineering student at Purdue, and I got kind of aggravated with having to try and explain things to her without the aid of being able to solve simultaneous nonlinear systems of equations. And so I kind of wrote the playground in part so that I could actually solve her problems and show her examples of how to solve problems and then just send it to her. So that's part of what was driving this. So anyway, if you want to go and look at other language playgrounds, I've listed a couple of them over here, but pretty much most major languages have a site that is a playground for that language. And we were just kind of missing that. So that was one of the things I was trying to address. So the goals for the project for me, apart from helping my daughter, helping to explain engineering concepts to my daughter, was to make something that was freely available. I mean, all these playgrounds are freely available. Allow people to use Modelica without necessarily having to install any tools. Make it easy to share your work, and that one comes from, again, me working with my daughter and wanting to send her something that she could run and see all the equations and see the plots and stuff. And so I wanted to be able to share stuff easily. I wanted to be able to support visualization. One of the very first projects I did with this was actually doing a sort of static analysis. Oh, here she is now asking for, no, I'm just kidding. Oh, sorry about that. Was to do a sort of static force analysis, static force balances, and then render that, actually render the vectors and show her how, oh, if you change this, the angle, of support on this thing, it's going to change the forces in this way and be able to visualize it. So that's why visualization was important. And I also wanted to allow others to create content. So as an example, this presentation is itself a piece of content that is being effectively rendered on this playground. I just walked up to this machine. I'd never used this machine before and was able to launch this because I had published essentially these slides and then gone to this playground app and then loaded them in. And I'll talk a little bit about how that's done. But the main point here was not to be able to give this presentation, but it was to be able to allow people, professors, for example, to be able to create content online that walks through all these things. And you'll kind of see how that works. And the last requirement was I didn't want any of these annoying cookie consent banners. So I'm not tracking anybody who's using this. Okay, so there's some analytics, but it's all anonymized. There's no personally identifiable information in here. I hate those things. And so I wasn't going to build a site that was going to immediately throw one of those in your face. Okay, so those are the goals. So the core of this is really this editor here, and you can kind of see it down here. This is based on something called Monaco. If you saw my presentation earlier today, this is what's used in Visual Studio Code as well. It turns out that there's actually not much overlap between the presentation I gave earlier today at the vendor session and this project. This is a personal project. It wasn't for work. And in fact, I wrote an entirely different Modelica parser and integrated it into Monaco, entirely separate from what the guys who did the work this morning did. And so this is using something called Tree Sitter. And you can, there's an implementation called Modelica Tree Sitter that you can go and get. This is a technology that GitHub uses to do syntax highlighting for pages in GitHub. And I don't think they're using my stuff, but I don't know. This also is compiles down to WebAssembly, which means it's very fast to parse the code. And one of the things that I did in this playground, and you'll notice if you're a sort of veteran Modelica person, is that there's no top-level model. There's nothing here that says model. And I did that kind of deliberately because a lot of these playgrounds, you want to start with just very simple things. So just declare a few variables, throw an equation, and go. You don't want to have to explain restricted classes and what's a block and what's an output and what's a model and what's a package and what can have constants. And I mean, there's all sorts of other things that you have to explain if you want to bring in restricted classes. So I wanted to start to make it really look like a program. Declare a variable, use a variable, instead of thinking about it in terms of models. So I'll give you an example here. Up here are some buttons. So this is the first one I'm going to talk about. This is the simulate button. So when I simulate the model, it goes off, it compiles the model, it simulates it, and then you can see the result here. So you see this value y, which is what we expect because we're plotting sine of y. You can also see that there's a little scrubber thing here, and you can see that there's a message here. It says our simulation or our solution for x was 20, and our solution for y depends on time. Currently, time is 0.02. Which means our solution is 0.02. But as I scroll this, you'll see that that's actually updating as I go, right? So it's sort of a live explanation. And if I change anything in this model and resimulate it, like the x, change that to 30, right? And then I just resimulate it. Of course, it'll change the message. And you also notice as soon as I change it that says now it says x is 30. And as soon as I change it, you'll also notice that it cancels out the results because it doesn't want to show stale results. It doesn't want to show you something that's misleading that doesn't correspond to the model that's there. So that's one thing. I'll come to how it does that stuff on the right in just a minute. But so that's the editor. There's no diagram viewing or editing in this tool. Okay, it's not that sophisticated, unlike the stuff I showed this morning. So Ricardo's tool sets do that. This is just a simple tool that I developed in my spare time, and so it doesn't have that. Now, in terms of simulation, we're using OpenModelica as the compiler behind the scenes, and this leverages a web API on a backend that I created to make simulation requests, and it's written in Go. It queues up jobs so that it doesn't get too overloaded, and it runs on a small Kubernetes cluster behind the scenes. So in terms of simulation, you saw an example of a simulation earlier, but I wanted to also point out that this platform allows us to use the Modelica standard library as well. So you can see here I import the Modelica standard library, and then I create a circuit here, and I create some initial conditions, and I have some connect statements on my machine. This all fits on one page, but here it doesn't clearly, but there's a bunch of connects in there. And so then, you can run a simulation. It goes off, it compiles it. One of the things about anything that includes the MSL is that it's going to take a little bit longer to simulate because it has to load the library in, but it wasn't too bad there. And so you get this plot, you can look at the results and see, okay, well, there's the sort of the second order response to this step function. You can plot other variables. I'll explain how that's all done in just a second. I'm just sort of working my way up there. So this is the simulation part. Don't think it's actually looking to see whether you import the Modelica library or not, and that's when it decides whether it needs to load it or not on the back end. So that's the basics of simulation. Again, you just press this button to simulate. So if we go to the next slide, I guess. So along the way, you've seen every time I run one of these simulations, you see some kind of, text on the side or a plot or something like that. So the question is, how's that done? So because you don't see that in the Modelica model, there's nothing in this Modelica model that indicates how the results should be presented. So instead, what I do is there's actually a couple of tabs up here, and I haven't really talked about that, but there's another tab here called report. So let me first simulate this, and then we'll talk about what's actually going on there. So this goes off again, runs a simulation, pulls back the results, and then it visualizes them. And you can see a couple of the different options you have here. You can show a chart and look at the values. You can show an SVG diagram of your system. You can show a 3D animation of your system. You can show plots using something called Vega, which is a pretty elaborate visualization library. So when I hit this play button here, these things sort of come to life. And so you can see, for example, the bouncing ball, right? So this is using the simulation results from here, and then it's translating it into this 2D animation of the ball, or in this case, a 3D animation of the ball. So you can actually spin around and see, you know, the simulated result here, this ball bouncing around. So the question is, how is this done? And so the answer is that all these visualizations I just showed you, all of them, are contained in this report. So I'll just show you the report. It's not too long, right? It's 48 lines long, and it captures all those visualizations. So the first one is you can make a chart involving one or more signals. So it's just a comma-separated list of signals. So if you include that in your report, then you'll get that result here. So that's how this is done, this visual. And it makes a nice plot and lets you, hover over things and stuff. The SVG that you see here is just a very simple SVG a tag really in HTML. The only difference is you'll see that the values are being injected here. Wherever you see these double squiggly braces, it's actually using something called nunjux, which is a templating language, to inject values. And so you can see right here, it's using the value of time right now, and then multiplying it by 25 and then adding 100. And then over here, it's using the value right now of H. So you can refer to this notion of now, which is tied to this slider up here. Or you can actually there's a function, built-in function called at. So you can say at 5 seconds dot H, and it'll give you the value of that. So when you write little reports, you put text in there and use Markdown, you can actually pluck out values from specific points in time as well. The 3D animation is using something called X3D, which is a kind of a standard, I guess. It's not standard in the browsers, but it's something that you can just include some JavaScript at the top of your page, and it'll go through and replace this declarative information here with a rendered scene, which is what's going on here. Okay, and the key point here is that everything in here is, and then here's the Vega version of my plot as well. But all of this is declarative, and the reason that I like the fact that it's declarative is that that's what allows me to inject these values in. I just describe the scene, and then I inject the values, and I don't have to write code that actually loops or does anything. I just write a single frame of whatever it is I want to look at, and then when I press play, I get the animation out of that. So so let's see. So going back to this, there's another point worth making here. If you look carefully, well, okay. So the pipeline here is that I do the nunjux processing, then I actually process any markdown code that's in there. Then I actually allow you to inject math. So you can put math equations, you can put LaTeX in here and it'll render the math. And then I do a bunch of HTML sanitizing for sort of security reasons. I don't want somebody to send you a link to this site that then, actually runs scripted content in there and sort of hacks your browser and mines Bitcoin or whatever. So I'm just trying to avoid all that with the sanitizing of it. So all of that's being done behind the scenes. You don't have to worry about that. You just write your little report and it'll worry about rendering all that through that pipeline. But another thing that's going on here, and if you look carefully, you may have already spotted it, is that you see this thing that says model up here. So let me kind of start over, give you a slightly simpler example to discuss this. If I go back to just, I don't know, the editor. Hold on, did I do this right? I don't think I did that right. Because it should reload this, just a sec. Let's go to the editor again. All right, so one of the things that you'll see here is that you see x equals 20 here, right? And you can actually take this link that's up here, copy it to your clipboard, and send it to somebody, and then they'll land right on this page. But even better is if you wanted to show them something different, like you wanted to change this to cosine, you can say cosine, right? You can modify this. You could even modify the report, right? It's our solution, say my solution, okay? All your changes are actually captured. What I mean by that is when you do this copy to clipboard, the new link actually embeds all that information. So what you will send to them, it'll be a ridiculously long link, but what you'll be sending to them is actually going to have the model you created and the report you created, not the one I created. So in other words, any modification you make to the content that's on that page is then captured in the URL, and then you can share it. It doesn't get stored anywhere. This is also part of the whole, I don't want to be responsible for storing your data because then I have to put a stupid cookie thing up on there. Okay, so this is all captured in the URL. All right. So anyway, so that's just kind of neat because basically anything you want to do at the playground, you can take a snapshot of and send to somebody. Ideally, I'm going to add a link shortener, but then again, I start tracking people's stuff. So that's, I'm still figuring out how to do that. But anyway, so getting back to this rendering thing, I just want to point out that any change you make to the model or to the report results in a custom link. Okay, and then finally, you have this notion of structured content. I'm clearly showing you something that's structured, right? There's multiple pages, there's a table of contents. All of that I created, and I've actually, in this case, I published it just as a gist on GitHub. And then what I did at the start, if you were looking, you see that here is actually the content. That is it, and there's a URL there. So I started this presentation by simply going up here, entering the URL where the content was here, and hitting go. And that's what launched this presentation. So the point is anybody is empowered to create a bunch of models and explanations and reports and whatever, publish them anywhere on the web. You don't have to publish them on my site. Publish them anywhere you want. And then you can just paste that URL in there. And when you do so, you'll get out a link that you can copy and give to somebody else. And that's basically, now it's your site. It's your content that you're publishing. So you can put in explanatory text as you see up here. You can put in a model to at least, to start with. You can put in a report template like you've seen before. You can put in metadata, which is what gives you all the titles and the table of contents in here. And you can even put in macros in there because these reports can get a little verbose. And so you can see here, the report here just says commentary for the time right now. Well, what is that commentary? Well, that's defined in the preamble. So that's not something that I'm not going to stuff that in here. That's just some predefined set of macros. And so you get this out because there's a macro in the preamble that defines what commentary means. So all of this is to be able to create, like I said, the structured comment. There's a bunch of, well, I wouldn't say a bunch. There's a few pieces of structured content already in the site up here. There's how to create lessons in here. And then there's also a tour of Modelica that I tried to create to demonstrate some of these ideas. So basic idea is I wanted to empower everybody to be able to create whatever they wanted to do here, animations, models, whatever. So in conclusion, I think this is really a long overdue thing for Modelica. It's a way that people can go and try out the language. It supports collaboration with this link sharing thing. I could imagine a situation where a professor could create a lesson like this and then send it to his students, and then they could actually like do the homework and then copy the link and send it back to the professor, and then he could just run their example right there in the playground because that link will point to their work, whatever they did on top of his work. And so yeah, people can build their own lessons or whatever, their own demonstrations of whatever they want to do. And just a couple final thoughts. I mean, ultimately, at the end of the day, models are software, and one of the things that I want to see is modeling become more ubiquitous. We want to see it in hardware and loop testing, in browsers, in CI/CD pipelines. So this is just another way of making the idea of models more accessible to people in general. And I think they deserve to have nice UIs and nice services around them and nice integrations with other systems. And so this is a way of being able to take something like a model and not make it so that it's locked in a desktop tool on somebody's machine, but instead to make it so that it's accessible and shareable to anybody. And so with that, I'm done. So my final simulation there. Thank you. And I guess I'll open it up to questions for whatever time we have left. Okay. Oh, Scott's okay. I'll start with Scott. I'll get to you, Chris. She doesn't care. As every parent knows, your kids are never impressed by what you do. So, thanks. Laura? Yeah, that's a good point. I meant to mention that. If you go back to one of these things that actually has some text in it, and let's say I use a variable called z that doesn't exist. So I can do a couple things that are wrong. I could add a syntax error, right? I could forget like a semicolon, or let's see, let's see what can I do here that would, well, let's do this one first. If I try and simulate this model, it'll give me an error, and it'll then highlight this. And if you mouse over it, it'll say variable z not found in scope. Okay, so it tries to, it'll give you whatever errors Modelica gives you if you simulate. But if you, even then, it should still detect syntax errors. So I'm not like equations, yeah. So I'm not, no, now it thinks that's a variable. I don't know. For some reason, I'm having trouble generating a syntax error. But if there's a syntax error, it'll know immediately. It won't even send it off to Modelica. The parser itself will detect that it's a syntax error, and it'll flag it. And it'll give you the same Monaco-based little mouse over thing. It even shows, if you look carefully, you'll see when it runs this that it even shows you this little red thing over here and the scroll bar, so you can figure out where on the thing. So this is all Monaco. I don't get any credit for this. This is Monaco does all that. Okay, so Chris, sorry, I was working my way across. I think you had a question.
So the front end is all WebAssembly, right?
Well, it's JavaScript that parses WebAssembly.
Where is the back end Modelica, right? It's Kubernetes, it's like, a Heroku thing, and like, is someone getting like a small little thing happens, where is it running?
It's running on a server that I set up. As with everything in the Modelica University thing, it's just stuff that I pay for in the background, but I gave away for free.
And how hard is it then for a student to just slot things into there, kill a program?
It would be very easy to launch a denial of service attack against my modest system here, which is why I prefaced my comment when I started up by, please just don't use it for the next 20 minutes, because it does have some degree of auto scaling in the Kubernetes cluster and stuff like that. But I mean, if somebody wanted to be malicious, yeah, they could bring the site down and make me pay slightly more every month because of the auto scaling than I already do. So it's not bulletproof by any means. I could probably put it behind like Cloudflare or something like that and gain some DDoS protection, but I didn't bother yet.
Well, yeah, that's kind of what it is. If this has a whole cloud connect, but that's where I thought, okay, we probably just got like one server back there, okay, everyone logged on the same one. But I guess that must also make the collaboration tools, right? Because they're all I guess it's searching more locally, or like would that collaboration actually work?
Yeah, well, it works in the sense that when you send a URL to somebody, then they bring this up, it renders their model and they're reported here. When they press the button, it still uses my backend. It's all my backend. No, it's not live. It's not live. Sorry. No. You could still do that with like WebRTC or something like that, I suppose. But no, it's not live. The idea is that I work on it for a while and then I hand it off to somebody else. So it's not using Git or anything like that. That's more the talk I gave this morning. Okay. Oh, wow. Okay. Yeah. It'll get really janky if you put too much stuff in there, especially a lot of things to draw and stuff. It's a React application technically, but it's actually, by using nunjucks, it's actually circumventing a lot of the optimizations that React would put into it. So you can if you do a lot of stuff in there, it's gonna get really kind of sketchy, right? It's not meant for large scale stuff. It's meant just for demonstrating concepts to people. No, I mean, it's actually just, well, I get that actually from nunjucks in the templating language, but I have to inject a few values, like the current value of the variables is associated with an object called now, and then I inject a function called at, which you could pass a number to, and it gives you back an object that has all the signals at a given time. So that evaluation stuff is really just nunjucks plus a little bit of environmental information that I hand off to nunjucks. They're just, yeah, it's got nothing to do with Modelica. It's actually it's just building in a set of signals. It's just an object with a bunch of string signal values. And it has an expression language, but again, those expressions are valued by nunjucks, not by Modelica. Well, the solutions are coming from Modelica. Yes. Sorry. The time series results are coming from Modelica. Yeah, I thought I had that on a slide, one of the slides, but yeah, I want to give the Modelica team credit because if I didn't mention that, I really should have. It's all running. Yeah, it's using Modelica for the compiler on the backend.
Language analysis.
Exactly, on the front end, yes. Yeah, so I'm just doing syntactic analysis myself. I'm not simulating anything. Okay, all right, one more, but I think then we've got to. So I can't hear you over the noise of this. Yeah, no, none of this is in the, again, that's the talk this morning, just to confuse people. Yeah, this, and the link thing isn't even Monaco. The Monaco thing is just the rendering and editing thing. I had to write the parser and then color the text, do the syntax highlighting, and then I did the link generation thing that's totally outside of Monaco. So that's just part of the app. Okay, all right, I think I overran, so I think I better stop it there. I'll hand it off.
Thank you so much. I think our next speaker is Mohammed Chawla.
I can't kill my tab because there's something in the way, so
That's all right.
Yeah. Permission is regarding
Yeah.
open platform for design and learning of cyber physics
Systems, cyber physical systems. Hello. We're gonna tag team the presentation. So me and my colleague Omar are gonna switch places at some point. So, bit of an agenda. I mean, it's the usual stuff: introduction, motivation. Then we're going to introduce the platform. I'm going to introduce this thing called Modelica Studio, which we realize there is a lot of overlaps with other talks, and you will see. Okay, so who are we and why are we here? These are our faces. In case you are interested, this is the team. We are a startup. We're called Perpetual Labs. The company is based in the UK. But we are actually kind of like a distributed team, a little bit sparse around the world. But we're also part of kind of like a bigger network. We are part of the open source Modelica consortium. We are part of open source project like Into CPS, Open Caesar. We are doing R&D collaborations with universities, with the European Space Agency, and we are doing some commercially led projects with the Boeing BA system and Airbus. So essentially, the mission of the company, the way we started, is to make modeling collaborative and accessible to as many people as possible. Very simple. The way that we want to do this, we created this platform that is called Gitworks. I'm gonna get into what Gitworks is in a second, but Gitworks is only kind of half of the thing. It's also like what's really important is we want to build a community around Gitworks that uses the platform as a nexus of collaboration and sharing of modeling. And ultimately, that's why we're here. We want the platform to be open. We want it to present to the Modelica community, and we want your feedback on what you think in what direction we should take, if what we are doing is interesting or anything of the sorts. Okay, so motivations. Has anyone heard about silos of data and knowledge? Raise the hand. I guess all this stuff is pretty usual. In the model-based design, we know there are silos of data and knowledge. There is lack of reusabilities of models and all that kind of stuff. Like you've heard these a lot of time, and that's why there have been several projects targeted at creating these platforms of interoperability to support collaborative model-based design of complex systems. I've cited here two projects: the Digital Manufacturing Commons and HubCap from Into CPS, just because they're recent. Plus, there are many more kind of commercial solutions out there, but I put these two here because they're open projects. They have not enjoyed as much success as like widespread success, and we are wondering kind of like why. And we identified essentially, if you want to do this thing of collaborative model-based development, we think that there are three major technical challenges. The first one is related to version control, change management, and traceability. As you are developing a complex cyber-physical system, you generate a bunch of what we call information artifacts. Think about requirement specification, system architecture model, Modelica models, design review reports, all that stuff. And unless you have a way to do consistent version control, change management, and traceability, this becomes unmanageable, and you cannot attribute who said what and when. To this, the solution we think is pretty obvious, is just apply Git across the scale to all your information artifacts. The question is that Git at the moment is really designed to deal with artifacts that are code-based. You can use Git to track your Modelica model, but what does it mean to do a diff on a Modelica model, for example? You can do it diff at the level of the code, but it's not really interesting. You would ideally want to do some kind of diff at a higher semantic level on your model. So that's what we mean by Git is it doesn't have the facility to deal with the typical engineering artifacts. So the Git model can be applied, but it needs to be kind of rethought and kind of like retooled around engineering artifacts. The other aspect is repeatability, durability, and efficiency. How many of you are familiar with the classic scenario, like you are part of a design team, someone sends you an email with design data in an Excel spreadsheet, you take those, you use them as input as your Modelica model, you run the simulation, get them out, when you do some post-processing, you send back the results. That creates the usual problem that the design evolves and you forget which version of the input data is connected with which version of the model, which is connected with which version of the results. We think that all of these should just be incorporated in continuous integration, continuous delivery pipeline. So you have the traceability, auditability of results, you build confidence in the results of your analysis, and you can have reusability of your design. And the last one is this idea that you know that you have a bunch of these information artifacts, and the knowledge about your system is spread across models, across reports, spreadsheet, all this stuff. And you know that you have variables in different models that are connected in some way. But you can define this translation at a syntactic level. But what would be really useful is that if you could define this connection between the variables of the different model at a higher level of abstraction, the level of the semantic, of the meaning. And then the syntactic translation are just derived automatically. And with that, we are looking at the semantic web. I don't know how many of you are familiar with the semantic web. It's this idea of moving from the web of data to the web of meaning by publishing on the web not just data, but the metadata associated that gives kind of interpretable meaning to the data. Semantic web has been around for 20 years, has gone through a little bit of a winter, but now it's kind of like coming back with Web3 and the Solid project. So we think these are the three major challenges. These are the three technologies that we think are key for these challenges. So what we have done, we take them, we shook them together, and what came out is this platform called GitWorks. And what is GitWorks? Essentially, first of all, it's a DevOps platform for digital engineering. Essentially, think GitLab, but for model-based design of cyber-physical systems. Plus, is a smart documentation environment. And I don't know if you're familiar with platforms like Notion, Coda, Airtables. They're kind of the next evolution of documentation, like the next evolution of the idea of Confluence and wikis. It's writing wikis, but they are actually backed by structured data and by databases. And we took that and we took this idea of smart documentation, but essentially backed by a knowledge graph, and we put it together with the idea of a DevOps platform like GitLab, and what came out is GitWorks. And essentially the objectives are to provide an integrated development platform for systems engineering designers and simulation engineers to manage their digital artifacts, create smart documentation, verify and share their models at speed and with confidence. Okay, so what does this look like in practice? The platform is divided in principally in three main environments. We have the GitWorks projects, and this is essentially version file management. It provides you with the kind of functionality that you expect from a Git platform, your branches, issues, merge requests. We're working on this idea of providing diff functionality as a higher level of abstraction, and it's something that perhaps we're going to roll out in the future. But then on top of the regular Git stuff, we have this idea of the semantic twin. The semantic twin is a play on this idea of the digital twin, and it goes back to that idea of using this higher level of abstraction, the semantic level, uses semantic web technologies essentially to create a knowledge graph of all your system-related information that becomes the nexus of communication, interoperability between the different modeling and design artifacts. And the semantic twin environment comprises of an ontology editor environment and a knowledge graph exploration where you can interact and query this knowledge. And then we have a CI/CD, kind of like continuous integration, continuous delivery environment where you can automate your analysis and results delivery workflows. And you can have, like, you can include in these analysis pipeline stuff like Modelica simulation, analysis with R, with Python. You can include Dockerize stuff. And hopefully in the future, we're going to expand the range of tasks that we support in these pipelines. And the idea is also that the runner, in this case, so here is the GitLab runner, but the idea is that for the pipelines that are computationally expensive because they have analysis like optimization or uncertainty quantification, we can connect with a scalable HPC solution. Okay, and then we have the second kind of environment. The platform is called the GitWorks Commons, and the Commons is really the nexus of interoperability between projects, and effectively is a package register on pair with stuff like with what NPM is for Python and Maven for Java. It's essentially a place where a project can package their models together with the semantic metadata and publish it on these registry, and other projects can import it by declaring it as a dependency, and you get stuff like facility, like model coded languages like dynamic versioning, where you can just depend on a particular version or get the latest one, and you have that kind of flexibility in reusing someone else's model. Okay, the last part is the IDEs, but Omar is going to tell you a little bit about that in a second. We have a case study which we did in collaboration with aerospace companies in an R&D project in the UK. This is focused around two companies, an OEM and a supplier. The OEM is kind of like designing the plane and the environmental control system for the plane, and the supplier is providing this component called the passenger air conditioner. And what that workflow looks like, or would look like in the platform, is the supplier as the OEM, in this case, has his own model, like he has requirements in something like a requirement model indoors, in a system architecture in SysML, and maybe he's doing some flight path simulation in Simulink. Now, through the adapter that we have created for these tools, this kind of like system level knowledge can be extracted from this tool, and a structured formal document can be created and published to the semantic twin. At the level of the semantic twin, this knowledge can be queried and again packaged in a formal documents that is the evaluation specification. Essentially, is a formal document that tells the supplier, this is what you need to make. These are the information you need to give me to validate your design. And the supplier maybe does as a Modelica simulation of these system of the passenger air conditioner, does some generates some results, and these are packaged again in a formal data document with the semantic metadata that is published to the semantic twin. And from that, through a query mechanism, a validation, first of all, there is a pipeline that runs a script that does the verification. So it uses the data from the simulation from the supplier to verify that their design meets the requirement based on what has been specified by the OEM. And this is then, and there is a report that is generated that goes back to the OEM. We have a lot more about this in the workshop. We're going to go in a lot more detail about how this works in the workshop on Friday. So if you're interested, you're very welcome to come and have a look. And now Omar is going to show you a little bit under the hood what the platform does, and also why we are here and we are interested in Modelica.
Yeah. Okay. Thank you, John. Yeah. So here to talk about the GitWorks implementation architecture. So for the GitWorks Commons, we're leveraging a lot of the GitLab functionality for this. So GitLab provides GitLab packages, right, which is an API that is package standard agnostic. So it supports things like NPM packages, Docker, Python, et cetera, and more plugins get implemented as we go. But one of the limitations of this is these packages are generally seen as black boxes. So in addition to providing the commons, we want to serve as like a knowledge broker for models, data, et cetera. So in addition to providing this kind of package functionality, we also enable semantic discovery and integration based off of these adapters that we've developed that extract these model data and convert it into RDF. And more information will be described in the workshop, but for this we use an intermediate language called OML, the ontological modeling language developed at JPL. So that's in order to support the semantic discovery and integration, we use that. We also are investigating monetization strategies. And so a lot of this was inspired by the what they call the digital manufacturing commons. And so we want to be able to entice modelers to go ahead and publish on our platform and enable them to make money, et cetera, whether by invocation or computational time, et cetera. I think that's a viable or necessary kind of feature that this kinds of platforms require. In addition to monetization, so this comes along with IP protection as well. So we were investigating co-simulation type things where we can go ahead and provide the results of simulations without actually having the users have to download the actual model IP. So that's for the commons. We have the GitWorks projects. So think of this, right, like John said, this is essentially DevOps for cyber physical systems. Again, we wrap a lot of the functionality that GitLab already provides, but we go further. So it contains a Git repository for versioning, as well as DevOps functionality, things like Git runner for running like CI/CD tasks. We extend that with an ontology management environment where you can go ahead and define custom types and provide links between different types of artifacts, whether in your CAD model or your Modelica model, et cetera, using this OML language. And then we pair that with a version triple store that we actually developed in-house, extending the TDV2 from the Jenna project to support materialized versions to support fast time travel queries based on your data set. And so for every commit in the repository, we have an associated triple store for that particular commit. And the data itself is generated by a variety of different adapters. And so for the GitWorks adapters, we currently developed a Modelica OML semantic web adapter that takes the Modelica model, extracts the information, right, and dumps it into the triple store that can then be queried essentially to support things like the semantic discovery and integration. And then we also have integrated with the Hartree Center, or collaboration with the Hartree Center, an HPC cluster based off of Slurm. And so that project is called Ugly. And this allows you to do things like uncertainty quantification that might require a large amount of resources that can't typically be done on like desktop machines. And so we provide that built into the platform of GitWorks. And so that's the overall platform. You can see the architecture. We're leveraging GitLab, which is open source, liberally licensed. It's MIT licensed, which is awesome. And Jenna for the graph store that we implemented a custom extension to support versioning. And then I think that's hidden here, the Slurm cluster as well, the foundation. And then we also, we developed, okay, so there, in terms of the GitWorks IDEs, I think a lot of the trend is trying to push to this kind of like open access, web-based kind of thing where you don't have to download these kinds of tools. I think we saw several examples in the previous sessions. And so this Visual Studio Code for web is an awesome platform. It provides a large ecosystem for manipulating various types of files. So it integrates Git version control and supports things like real-time collaboration, which is awesome. And so we developed the very first extension based off for Modelica, essentially, and we called it Modelica Studio, right? And so it's browser-based, and it supports both synchronized text and diagram editing. Well, currently it supports viewing, but we're working on getting the editing also working as well. It's an open core project, so this is developed in collaboration with the Open Modelica Consortium. So the project is based off of this frontend.js, which Perpetual Labs really led the development on. And it's a standalone JavaScript library for incremental error-tolerant parsing, as well as lazy flattening of Modelica models that all occurs in the browser. So there's no cloud component in the backend that's required for generating these kinds of diagrams. And so the library itself, frontend.js, also generates the diagram and icon SVGs, right, to support that all in the browser. And it's also used for our adapter for converting to OML. So that's the highlight, I think. And then we're also developing a heavyweight workspaces that can deliver kind of like VDI, virtualized desktop infrastructure over no VNC. So things like, the traditional desktop applications, if they want to be accessed over the web browser, we want to be able to support that as well. So that's another component of the architecture. I have a short video here. We can show. Oh, hold on. Let's actually go back. So in this screenshot, you can see one of the functionalities of, how do I go back? You can see in the screenshot, one of the functionalities of having this, the flattening all occurring in the browser is it's very easy to integrate the live share extension, because the live share extension essentially functions based off of text. And so all it's doing is synchronizing the text deltas across multiple users, and each browser essentially is re-rendering the diagram. So providing these kinds of editors completely in a standalone browser environment kind of simplifies real-time development. So you can see multiple cursors in the screenshot, editing the model at the same time. And here's another example. I have a video how this works. Let me see if I can speed things up a bit. So I took the Chua electric. I don't know if that's pronounced correctly, but you can see here. So it's fault tolerant. We introduced an error, right? It automatically highlights that as an error, and it doesn't break, or it doesn't break the actual rendering for the most part as well. And so you can go ahead. You can see we changed, for example, the rotation. It rotates the components, and all of this rendering is actually happening on the browser. There is still some work. You can see that there's some artifacts, some errors in the rendering. We plan to have that fixed, but for the most part, the incremental flattener is largely developed, and all of the libraries are downloaded incrementally as well. So we don't download so all the libraries that you might depend on. In this case, we have like two different libraries. We depend on the Modelica standard library 4.0 and the custom Perpetual Labs library. All of them are downloaded in a lazy fashion and instantial. What they call flattened, I guess, on demand as things happen. So that speeds things up, and we're taking advantage of caching on the browser as well. And so you can see so now we're entering the equations, and you can see the lines, the connections essentially being drawn here. Let's see if I can see speed things up a bit. Yeah, and so you can see the color, for example, we can manipulate the color as well. So all of this is happening within the browser in a lazy fashion and incremental. So as part of this project, we developed a tree sitter parser for Modelica, and we developed this frontend.js, which does the lazy instantiation of these Modelica models. And this is an example that we developed. And we also have the adapter that converts these models into an OML representation that gets compiled down to an RDF and stored in the triple store to enable these kinds of functionality. Yeah, and so I think that, so another error, for example, here, you can see that the squiggly lines get integrated. But essentially, we have the entire model essentially partially flattened, and we can provide a lot of information directly in the browser based off of that. So it doesn't have to hit the cloud. And so this is highly scalable and something that we intend to offer free to users on the GitWorks platform. Had we done a traditional, so there's several other, I guess, implementations out there, right? Most of them hook up to a cloud-based thing, but the problem is it's not scalable, right? And it can be difficult to offer to a lot of users. I think the previous speaker mentioned it's very easy to hose the server if multiple users, I guess, are submitting, complex jobs at the same time. So that's I guess, one aspect. So let's go to the next slide. I think, yeah, so conclusions. Did you want to take this? Yeah, so yeah, we presented our vision for the GitWorks platform to enable the collaborative model-based design of cyber-physical systems. We proposed this system architecture for GitWorks, and we developed a prototype implementation that focused on around enabling the use of Modelica in the larger MBSE process. So that's essentially one of the most important ideas that we're trying to push. And then we also conducted a preliminary case study, right, like we showed, and then plans for future work include the development of these adapters, not just for Modelica, but other types of artifacts as well, and also IDEs to increase the number of different modeling paradigms and cost tools supported by the platform. Things, again, like the NOAA VNC platform, et cetera. And then we're also working on, making the user interface more mature and demonstrating, the application to other use cases, including satellite systems design and manufacturing. So a lot of good stuff in store, hopefully. Thanks for your attention. I guess any questions? 2 questions, okay. Yeah. Say it again. It's a web-based tool. So I think John can maybe perhaps discuss that in a little more detail, but one of the ideas is a lot of this stuff is open core, right? So the core kind of functionality, the algorithms that we're using, it's an open source platform essentially, or open source projects that we're leveraging in the platform. And so that I guess that helps with the longevity, I guess, of the platform. We're also pursuing commercialization as well. But do you want to speak on that?
Yeah. Okay, so our last speaker was at Gathering. He's the associate professor for modeling science and his production topic is enhancing SST preparation using SST demo.
I sent it on email, the presentation. I think it should be probably so. Yes, okay. Hi, and welcome to this presentation about enhancing SSP creation using SSP Gen. My name is Lars Hattelal, currently an associate professor at NTNU Ålesund in Norway. And for the last few years, I've been developing a lot of enabling tools related to co-simulation, with SSP Gen being one of them. Firstly, some quick background information. Co-simulation refers to an enabling technique where different subsystems making up global simulation are modeled and run in a distributed fashion. And this technique has seen quite some use within NTNU campus Ålesund since 2014 and onwards, in order to mainly simulate maritime systems. And we use the functional mockup interface to represent individual models, and FMI is basically the de facto standard for co-simulation today and should need no further introduction. But however, for representing the whole system, we use the system structure and parameterization standard, which I'll briefly introduce more about in the next slide. So the SSP, that's a tool-independent standard tool-independent standard managed by the Modelica Association, just like the FMI, to define complete system consisting of one or more models, including its parameterization that can be transferred between simulation tools. And then in this context, a model is most likely to be a functional mockup unit, or just FMU, adhering to the FMI standard. An SSP, that is basically a zip archive that includes an XML file describing the system, its connections, and parameter sets, together with any data that is required to run the system. So basically, the FMI allows individual models to be transferred between simulation systems, while the SSP enables this for complete systems. And therefore, the SSP allows us to easily test the same simulation in different tools, even with different orchestration algorithms. And this is very valuable for comparing and evaluating systems. Now, in order to accommodate co-simulation at NTNU Ålesund, we have developed a lot of enabling tools over the last few years, all of which are open source. And this includes both low-level software packages for importing and exporting individual models, and also higher-level libraries and tools for orchestrating complete simulations. And SSPGen, which is the focus of this talk, fits somewhere in the middle and was made to make it easier for the team, which have different backgrounds, to store and share simulations. And by conforming to the SSP standard, SSPGen is a domain-specific language that can be used to produce tool-independent descriptions of a simulation, which later can be loaded into a growing number of SSP-compatible orchestrators, including the one shown here. So prior to SSPGen, we wrote basically ad hoc simulations in code. And we even created SSP archives by hand, writing XML and creating the zip folder manually. Naturally, this is both time-consuming and error-prone. So next, I want to introduce the topic of domain-specific languages, or just DSLs, as we have mentioned that SSPGen is one. So in short, a DSL is a computer language specialized to a particular application domain. In this case, the SSP standard. A DSL is created specifically to solve problems in a particular domain, and it's not intended to be able to solve problems outside of it, in contrast to general purpose languages. And usually, DSLs make the code more readable, almost like a spoken language. And this means that even people who don't understand the architecture behind the code should be able to understand much of its meaning. And DSLs implemented via an independent interpreter or compiler are known as external domain-specific languages. A well-known example of this include LaTeX and CMake. A separate category is known as embedded or just internal domain-specific languages, and are typically implemented within a host language. And they are typically implemented as a library and tend to be limited to the syntax of the host language. Perhaps a well-known embedded DSL is Gradle, used for building Java-based applications, which utilizes Groovy and runs on the Java virtual machine. Next up, I want to mention Kotlin, which SSP is written in. And Kotlin is a modern object-oriented programming language known for its readable, clean, and concise syntax. Perhaps most known as the default language for Android development nowadays. And Kotlin can run on the Java virtual machine. It can transpile to JavaScript or even compile to a native target. But it's probably mostly known to be used as a drop-in replacement for Java. With its advanced functional programming capabilities like lambdas outside of parentheses, and lambdas with receivers, we can create type-safe, statically typed builders that pretty much act as DLLs using Kotlin. So this allows us to create a natural domain-specific language while having access to the entire Java ecosystem, and additionally the tooling that Kotlin has. So good tooling is a key to efficiently and correctly apply a domain-specific language. In that respect, I do recommend IntelliJ, integrated development environment, to edit and run Kotlin scripts. So finally, more about SSPGen. So in short, SSPGen is a Kotlin domain-specific language for easing the creation of SSP 1.0, the current version of SSP, compatible systems. So rather than creating zip archives consisting of XML and other files by hand, we can use SSPGen, which introduces a natural and easy to deploy DSL that creates the necessary XML, and also it handles the packaging of any referenced files into the zip archive. And more importantly, SSPGen automatically checks that the SSP configuration is valid, so that any logical errors is caught prior to simulation. And furthermore, the SSPGen DSL is a library that is available through Maven, the de facto standard package manager for Java, allowing it to be referenced directly in these Kotlin scripts that I mentioned. So therefore, SSP systems using SSPGen can be distributed as a single executable source file, that is a script, making it very easy to modify the system to simulate. And as we are working with an embedded DSL backed by Kotlin, we can also make use of any external libraries written in Java or compatible with Java in this script. And we can, of course, use expressions to represent values, whereas if we use plain XML, such values must be hard-coded. And furthermore, SSPGen allows files to be referenced both as local files, and also we can use URLs, where, of course, using URLs helps improve portability. It's much easier to share a text file with URLs instead of having to share a folder, including the files as well. So SSPGen, as mentioned, is written in Kotlin. And a nice thing about Kotlin code is that it has the ability to be executed as standalone scripts. So this is one advantage it has over Java, that it can actually be executed as a script. However, to make this work, you will need a Kotlin compiler on the target PC, but anyone with IntelliJ installed, which is free to get, you will get the compiler automatically, and you can run the script from within IntelliJ by just right-clicking. And this works just by installing the integrated development kit. And it also, of course, provides syntax highlighting and code resolution since Kotlin is a statically typed language, so the DSL that you write will also benefit from that. And again, we recommend using IntelliJ when working with SSPGen. So the image here is just an example of some random DSL using Kotlin. Another nice thing about Kotlin scripts is that they support runtime dependency resolution. So unlike, for example, Python scripts, which have prerequisites, if it uses a library, you have to install it first. With Kotlin scripts, it will get resoluted runtime. So you don't need to have the library that you use installed beforehand. Kotlin will, using Maven, fix this at runtime. So this allows us to share SSPGen scripts without requiring pre-installed libraries. The recipient will need a Java developer kit, however. So that's a requirement to run these scripts, that you need a Java development kit. So here we see the anatomy of a SSPGen script, and those familiar with the SSP should recognize many of these elements. So we depend on, in this Kotlin script, we depend on SSPGen, and we import it, and then we create an SSP, we give it a name, we say what resources we have, so it could be files, it could be URLs, and then we basically define the XML, the SSP. We give the name, we give it some attributes, we create a system, we add elements, which here are components, that is FMUs. We assign connectors, we have parameter bindings, and we create connections. So these are all elements that you find in the SSP, just here in a DSL format. And of course, here you can open this in IntelliJ, right-click, and it will download the files. It will build the archive. So you end up with a file .ssp, which you can load into some simulation framework. So this is quite hard to see, but what you see here is that we have an SSP system modeled with SSPGen in the context of IntelliJ. So you have syntax highlighting and all that. By right-clicking here and run, you will end up with the XML you see on the right. Of course, the XML is packed into this zip folder, which is the SSP as well. Next, I want to talk about one of the novelties of SSPGen, which is integration with the Open Simulation Platform's interface specification, or just OSP-IS. The OSP-IS is an addition to the FMI standard, which provide a method for adding semantic meaning to model interface variables. It provides a simpler model connection process, and it makes it possible to do validation of semantically correct simulations. And this works by supplying an extra file with metadata alongside an FMU, something that could be improved using FMI 3.0 capabilities in the future. The OSP interface specification should not be confused with the OSP system structure, OSP-SS, which is an alternative to the SSP for describing simulation systems. The OSP-SS, however, it does support OSP-IS natively, but libcosim, if you've heard of that framework, is the only co-simulation library that supports it. So therefore, the OSP-IS is only usable in the context of the OSP initiatives libcosim. SSPGen, however, is able to transpile compound OSP-IS connections to single scalar connections supported by the SSP, and therefore allowing OSP-IS to be used outside the OSP project in any tool supporting SSP. So additionally, SSPGen is able to verify the connections according to the OSPIS, and this is done at creation time, allowing errors to be caught immediately. In the OSP workflow, the OSPIS has to be verified independently in a separate tool called the OSP validator, alternatively during runtime. So SSPGen does this process a little bit more streamlined, and it opens the OSPIS to more tools, which is great. Other features of SSPGen is, for instance, support for proxy FMU. And proxy FMU is a tool for distributed invocation of FMU supported by some co-simulation orchestrators. And SSPGen recognizes proxy FMU URIs and will validate the underlying FMUs model description the same way as normal FMUs. SSPGen also integrates with Python FMU, a package for writing FMUs in Python, allowing users to build FMUs on demand by just pointing to a compatible Python script. And this makes it very easy to rapidly change the behavior of such FMUs in between builds. Also, SSPGen integrates with the FMI VDM model developed by the Into CPS project, which enables additional static analysis of the included FMUs. For example, in order to check if the reference FMUs comply with the standard as they should. So the conclusion here is that using SSP, simulations can be defined in a standardized way, and SSPGen makes them easier to create, modify, and share, which, for instance, may make bitrot less of an issue as the system becomes more transparent and easier to reason about. It enables complex parameters to be defined, for example, based on some equation, or you can even do pre-simulations in the script to give you the value that you need for some parameter. Furthermore, it enables the OSPIS to be used in an SSP context, making it usable by a larger audience, which is great. And finally, onto some future works. While SSPGen is quite usable in its current form, it could always use some additional polishing and more tests. And also, the support for SSP version 1.0 is not 100% complete. It has the most used features. So if you as a user see something that's missing, just let me know and we will figure that out. And finally, as FMI 3.0 has been released, we should add support for that. And similarly, so should any updates to the SSP. And that was SSPGen. Any questions? Yes, do you control it or?
So, this was project. And this is like large scale simulation on homework.
So it was it's a project that's delivered basically this libcosym library, and it supports both SSP and also the OSP access. So the OSP decided that they wanted something to create easier connections. So instead of just using SSP, they created this OSP system structure. But I basically shown through SSPGen that, okay, perhaps it wasn't necessary to create OSPSS. You could use some DSL to make the connections easier by still using SSP. But you can use both.
I mean, would you consider participating in the SSP project? Because, I mean, there is also on work with that monastery, and I mean, doing what you're doing, that seems like, in terms of this open simulation platform, related work, that seems like very philosophical. I mean, I'm speaking here with my Modelica association hat on and think that they can definitely use some input from other industries, because basically at the moment everybody in the project only comes from automotive background. And you have the complete platform in a different industry, and I think that would be really useful.
Yeah, of course. It's something to think about. But it's quite nice to just sit back also and relax and let someone else handle the discussions. But yeah, something to do.
I mean, I think it would be very useful because I would think that the SSP, I mean, the current SSP project is a little bit maybe not opening the eyes wide enough, because they only have automotive companies visiting. And I would see SSP as much more broadly useful. They simply let somebody that brings them the right requirements, which, I mean, they're probably not vastly different. SSP is useful as is. But as they are working on the next versions and integrating FMSP, I think it would really be helpful. Even maybe just as a guest or observer at the beginning. I mean, but I think it would be.
Yeah, absolutely. Was there any other?
It's not important. You said the word signing.
Yeah, I got the question. So first thing first, the OSPIS is completely optional. So you can use SPGem, which is this library basically, which you can use in a scripting context to declare your entire SSP thing. So you declare what this SSP should contain, what they can use, how they are connected, the connectors and so on. So you define everything using this DSL instead of writing the XML. So it makes it easier to create SSP, and then you can choose to use this OSPIS that I talked about to define the connections. But you can, of course, just write single scalar connections between anything, just like you would do in the XML for SSP.
And we have the parameter handle, for example, the SSP files along which are normally embedded in the SSP. So do you also provide something like that, or
If I remember correctly, it will always export non-SSV. So it will be embedded inside the main file. So it will, as it is now, it will never generate that SSV.
so it's pretty much the SSP?
Yeah, so you get the system structure.xml inside the zip archive to get any FMUs that you use as a resource folder, and of course you can add other types of files in there, text files, and so on.
If there are no more questions, I think we can end this session, and that's time to get for the speakers.